So what we're asking for here is we have a pre-cut stud that is 92 5/8 inches long. If we're framing a wall, there's a 1.5 inch bottom plate, or sometimes called a shoe, and a double 1.5 inch top plate to construct the wall. So what that's saying is we have our studs that are 92 5/8 inches. On the bottom, it's often just referred to as a bottom plate. The technical term is a shoe that is 1.5 inches. And then on top, we do a double top plate. And each of those is also 1.5 inches. So we need to find the total height of this wall. That's simply going to be adding the 92 5/8 plus, well, we have 1.5 inches 3 times. So rather than adding it 3 times, let's multiply it by 3. Well, if you guys recall from Friday, multiplying mixed numbers is no fun. So how do we avoid multiplying mixed numbers?
Make it an improper fraction.
There we go. Make it an improper fraction. So 1.5 becomes how many halves? 3/2. Good. Perfect. And then when we multiply that by 3, we turn the 3 into what? 3/1. Yeah. So then we multiply. 3 times 3 is 9. 2 times 1 is 2. 9/2, which will reduce to 4 1/2. So then to add these 92 5/8 plus 4 1/2, we need a common denominator. What will that common denominator be between eighths and halves? 8. Good. So the 5/8 doesn't change. 1/2 becomes how many eighths? 4. Good. So we'll go ahead and add. 5/8 and 4/8 makes 9/8, which of course is 1 1/8. So we keep the 1/8 and carry the 1. 1 plus 2 plus 4 makes 1 plus 2 plus 4 is, careful, 7. You gotta remember the 1 that we carried. Okay, and then we have the 9. So it's 97 1/8. Now this is actually the typical framing for what we refer to as an 8-foot wall. How many inches are an 8 foot? What's 8 times 12? 96. Good. So what is typically referred to as an 8-foot wall is actually 1 1/8 inches more than 8 foot. It's 8 feet, 1 1/8 inches. Why is it different? Why is it not 8 feet? Exactly. Well, 1 is ceiling covering. Ceiling covering is just a fancy way of saying the ceiling sheetrock. The sheetrock on the ceiling is typically 5/8 of an inch because roof trusses are typically 24 inches apart. The sheetrock has to be thicker, so we use 5/8 sheetrock so it can span the 24 inches without sagging. 1/2 inch sheetrock will start to give you a little bit of a sag on 24 inches. So if I have 97 1/8 inches and I subtract the 5/8 inch sheetrock thickness, What do we get there? Well, we have a common denominator, so we don't have to worry about that. But 1/8 minus 5/8 can't be done. So what do we have to do?
Minus 6 and 9/8.
Perfect. We borrow from the 7, that becomes 6. We add 8 to the 1 to make it 9/8. Great. So now we'll subtract 9/8 minus 5/8 is 4/8, which of course can reduce to a half. And then we got nothing to subtract from the 96, so it's 96 and a half. It is still a 1/2 inch more than 8 foot. Well, if you go into just about any home, if you measure the ceiling height, floor to ceiling, it will be slightly more than 8 foot. It won't quite be 96 and a half because you have your finished floor underneath, whether that's carpet or some sort of luan and linoleum or tile or whatever. But it will be more than 96. And the reason for that, so we have our wall here that's 97 and 1/8 inch. We put in our 5/8 sheetrock here, leaving us with that 96 and 1/2 inch here. Well, typically you're going to cover that wall with sheetrock. And sheetrock comes in sheets that are how wide? The width of a piece of sheetrock is 48 inches, typically. You can buy them wider. You can buy 54-inch sheetrock for 9-foot ceilings, and you can actually buy 5-foot width sheetrock for 10-foot ceilings. It's really expensive to get the odd widths. So that's 48 inches there, and another 48 inches. That gives us actually a 1/2 inch of clearance on bottom. The reason for that 1/2 inch of clearance, well, there's several reasons. One is in case there's any unevenness in the floor, any lumps, or hopefully you're not, your floor should be flat, but if there is any unevenness, that keeps it from catching. Or if any of your flooring screws stick up, it doesn't catch on those when you put it in. So it gives you clearance so you don't have to trim the piece of sheetrock to get it in there. The second reason, when you mount that bottom piece of sheetrock, in order to get it tight to the top piece, you use something called a foot jack. So you have your top piece of sheetrock here. To hold the bottom piece up, you're not going to get your fingers underneath it. So that foot jack is a tool that sits on the floor. It looks something like this. So you actually just set your foot on it, you slide it forward with your toes, get it underneath the sheetrock, and then just press your heel down and lift it up. So you need that clearance to get the tools underneath there to lift the sheetrock into place. And then the third reason is a very practical one, but very important, for moisture. If your floor gets wet, and in Wisconsin, floors do get wet, that 1/2 inch clearance keeps the bottom of the sheetrock from getting wet. Because sheetrock, unfortunately, has an organic factor to it, which means if you mix it with water, it becomes food for mold. And mold is I don't know if you ever lived in a house that had mold and had to be removed. It is a pain to get rid of. Okay, so anyway, the reason I wanted to go through the height of a stud wall is because the exercise we're going to work on today is we're going to look at stairways and how the math behind a stairway fits in with our fractions. As always, when I draw pictures, you might have to use a little bit of imagination because my drawings suck, but hopefully we can get the point across. We'll start off with a little bit of vocabulary. So this is our lower level floor. Of course, this then will be our upper level floor. The height from the lower level floor to the unfinished ceiling above is the lower level ceiling height. I'm typically just going to call that ceiling height because the upper level the height of the ceiling in the upper level doesn't affect our stairway. So if I say ceiling height, we're assuming it's the lower level. On our staircase, this piece right here is called a riser. So when I refer to that, you might hear me call it a riser height, or sometimes called a unit rise. Architects tend to call it a unit rise. Most contractors refer to it as a riser height. Both are accurate. Riser is just kind of the slang term used on the job site, or the unit rise is the technical term used for people that don't do a lot of building, to be honest. Then we'll have this dimension right here. That piece is called the tread. So we'll refer to the tread width. Width is that dimension from the bottom of the riser out to the toe. Or, again, the architectural term is sometimes called the unit run. We'll talk about some standard dimensions for those in just a little bit. This hole in the upper level floor is called the stair opening. And then the important one, which I didn't draw very well, I'll draw actually another set of steps over here. The distance from, and technically it's the plane of the stairs. We'll try that again. So it's a line that connects the very tip of the stairs. The height that we have to go from that line up to the bottom of the ceiling at the edge of that stair opening is called head clearance. Most of you, if you haven't already, at some point in your life will be in an older house where they didn't bother worrying about the head clearance, where you've either got to lean way back, or I go into a number of old homes where I have to turn around and go down the stairway backwards because I've got to duck down so far. I can't get my head underneath it. Not having proper head clearance is a big pain, and it's actually a major code issue now. It's one of the things that most building inspectors will check on a house. Minimum head clearance by code is 6 feet 4 inches. Now there's a couple of things that come into it. This is finished head clearance, which means that's after any sheetrock is applied or trim that might be used to trim the edge of that opening up above. And if you put any carpet on the stairway or any sort of finished flooring on the stairway. So typically what most contractors will do is they will go at least 6 foot 8 inches. The main reason they use 6 foot 8 is because that's your standard door opening. So it makes the stairwell consistent with a door. Some will actually go up to 7 foot 1 because 7 foot 1 guarantees you can actually just measure off of the step below it and go up, and it guarantees you have the clearance from that plane, that line of the stair noses. So when you hear me say the nose of the stairs, all I'm talking about is that little point right there where the tread and the riser meet. So risers, typical risers are about 7 inches. We want to try to stay as close to that as we can. We can adjust slightly up or slightly down. Code allows us to be between 6 and 8 inches for a riser. Tread usually is about 11 inches. code used to allow, I think, from 9 to 12, and I think they shaved that back now. I don't think 9 is allowed anymore. It's been a couple years since I looked at the current code, so I'm not exactly sure where we're at as far as the minimum. But I believe it's 10 to 12 inches now is what's allowed rather than 9 to 12. We typically shoot for 11, 10 and a half, whatever makes things fit into the spacing we're looking at. So the first thing we want to look at is we want to find total floor-to-floor height. Which I just realized I did forget to give you one of the dimensions here. One of the dimensions that plays into that total floor-to-floor height is our floor thickness. Now that floor thickness includes finished ceiling on bottom, finished floor on top. If you're using a 2x12 floor joist, it typically is right around 12 inches because your floor joist would be 11 1/4. Of course, we all know 2x12 isn't 12 inches wide. And then your 3/4 of an inch tongue and groove sheeting on top brings it to almost exactly 12 inches. A little bit more if, with finished flooring and stuff like that. When doing a stair riser calculation, we often ignore finished flooring because, yes, the finished flooring is going to raise up the flooring in the upper level floor, but if you're going to finish the stairs, that finished flooring raises the level of each of those treads on the way down as well. So let's say we have a floor that is 12 3/8 inches thick. If you use an I joist instead of a 2x12, I joists are 11 7/8. Actually, it should be 12 5/8 inches thick. There we go. A ceiling height of 97 1/8 inches, as we calculated before with our standard stud wall. How do I find my total floor-to-floor height here? Don't be shy. Just add them. There we go. It is that simple. I don't know what it is. No matter how comfortable you are in the classroom, you put the cameras on and everybody gets quiet. So I understand. So 1/8 and 5/8 add to make 1/8 and 5/8 makes 6/8, which reduces to 3/4. 7 and 2 makes 9, and 9 and 1 makes 10. So 0 carry the 1. So 109 3/4 inches is our total floor to ceiling height, or floor to floor height. Why is that important? Well, because we need that total floor to floor height to calculate our number of risers that we're going to need to get from the lower level to the upper level. And to do that, we start out with a estimated rise, which I set up above. Typically, we go at 7 inches. So we're going to start with 7 inches. So we'll take our 109 3/4 inches divided by 7 inches. Now, for you guys doing this, hopefully you will have a fraction calculator to use, because this is not a pretty calculation to do by hand. But since I'm doing the work, let's go ahead and do it by hand. So 109 3/4 has to be changed into fourths. What do we have to do to the 109 3/4 to turn it into an improper fraction? (109 times 4, which is 436. Then what? Plus 3. Good. 439. Now the 7, of course, is just 7 over 1. Now what? Do the reciprocal. You got it. So 439 over 4 stays the same. It becomes times 1/7. Now 439 was the one, or 7, sorry, was the one number that we didn't have a good divisibility rule for. So let's just do 439 divided by 7 just to make sure it doesn't divide out, can't be reduced. Unfortunately, it cannot. So we'll multiply this out. 439 times 1 is 439. What's 4 times 7? 28. Good. Now, rather than doing our long division here of the 439 divided by 28, let's use the calculator to make that easier. So we'll do 439 divided by 28 gives us 15.67. And that is going to be risers. That's how many steps up we have to have for the staircase. Obviously, we can't have 0.67 steps. We need to either round that up to 16 or down to 15. So the question is, do we want it to be slightly larger than 7 inches or slightly less than 7 inches? You want it slightly larger, okay? If I want my rise to be slightly more than 7 inches, do I round the number of risers up or down? Careful. More risers would make them smaller, so we want less risers. So we're going to round down. I'd say 9 out of 10 of my groups that do this get that question wrong. So don't, it's counterintuitive that you round down to make it bigger. So we round down to 15 rises. So now we need the exact rise. So we still have to deal with the 109 3/4, which is the 439/4. And we have to divide by 15 rises. What do we have to do next? Reciprocal again. Good. So times 1 over 15. Unfortunately, 439 does not divide by 5 or 3. So let's multiply this out. 439 times 1 is 439 again. What's 4 times 15? 60. Good. So now we have to divide that out to get an exact rise. We're going to round it to the nearest 16th of an inch. When we're doing rough framing, generally if you're within an 1/8 of an inch, you're considered to be okay, but a 16th of an inch is really about as precise as you can be. So rather than actually dividing this out exactly, we're going to go ahead and just use the decimal equivalent. 439 divided by 60 gives us 7.31666 inches. To turn that into the nearest 16th, we just take the decimal part of it, the 0.31666. Of course, it would be 7 at the end. On the calculator, I do that just by subtracting the 7 off of it. and I make it into a fraction the easiest way I know how, and that's just by putting it over 1. Well, right now it has a denominator of 1. We want it to have a denominator of 16, right? How do we turn the 1 into a 16? Multiply by 16, good. So that's 16. We do the 0.316666667 times 16. We get 5.06. So that tells us it's between 5/16 and 6/16. It's closest to 5/16. So that is our unit rise, or our riser height. This is really close to being dead on 5, so we don't have to worry about any sort of correction as we go through. If we had like 5.3 and we were rounding it down to 5, well, then every third or fourth step we might put an extra 16th on it just to even it out, so we weren't off by a ½ inch or so when we got to the end of it. But so 7 5/16 will be our exact riser height. So that's what we want to make sure we cut our risers when we do our stringers. So I want you guys to try this in your notes. So we have a floor here that is, let's call it 18 7/8 inches thick. 97 1/8 inch will be our lower level ceiling height again. I want you to find, 1, the total floor to floor, the number of risers, and then the actual riser height. I want it to be slightly larger than 8. Slightly larger than 7 inches. I'll give you a few minutes and then we'll go over that. Okay, so you start out adding the 18 7/8 and the 97 1/8. And of course, that adds up to how much? 116, perfect. So then what are we going to do with that to find the second part, the number of risers? Well, we want it to be slightly more than 7, so we're going to start out by dividing by 7, which gives us 16.57. If we want each rise to be slightly more than 7, do we round that up or do we round it down? If we round up, we'll have more rises, so they'll have to be smaller. So if we want it to be a little bit bigger, we round it down. So we're going to have 16 rises. Now, the nice thing about having 16 rises is this is going to come out exactly on a 1/16 of an inch. To find the actual rise, we take our 116 inches divided by 16 rises. So 116 divided by 16, we get 7.25, which of course, we don't have to do the conversion. We know 7.25 is 7 1/4 inches. So that's our unit rise. Did anybody actually get that on their own? No? Okay. We're gonna keep working on that throughout the years, so don't worry. That's one of those that we'll keep coming back to. So the next thing we want to look at is head clearance. And we are going to do what for head clearance, we're going to use what is called the nearest step method. And what the nearest step method is basically saying we're going to just, instead of going through all the work of figuring out where this line that goes through the noses ends up at. Oops, or that's the noses of our treads. And we're supposed to be going off of that line. What we're going to do, what the nearest step method does, is it just says, let's just go off of the nose of the nearest step. So even if we're out here, we're going to go off of that nose. And that's what we're going to use to calculate our height so that we don't have to do, it'd take trigonometry to figure out where we were at along that line that goes on the tips of the noses. So we're going to go with a 6 foot 4 inch minimum head clearance. The reason I said minimum is because one of the other characteristics of the nearest step method is that we always end up with slightly more head clearance than the minimum. So for the stair risers that we just calculated, with a unit rise or riser height of 7 1/4 inches, the floor thickness was 18 7/8 inches. We are going to use, and this is the part I have to give you, a tread of 11 inches to get our desired clearance. We need to calculate a total drop. So the total drop is the distance from top of the floor down to the nose of that tread that we're going to be above. We know that the head clearance, this part here, has to be at least 6 foot 4 inches. Well, 6 times 12 is 72, plus 4 is 76. So in other words, it has to be at least 76 inches. If our floor thickness is 18 7/8 inches, if I just add those two, not as tough as it looks because we have 7/8 plus nothing, which would be 7/8. 8 plus 6 is 14, so 4 carry the 1. And 1, 1, and 7 makes 9. So we have 94 7/8 inches of total drop required here. So from the top of the floor down to where we're measuring on the stairway, we have to have 94 7/8 inches of total drop. So we need to have the number of risers required to get that total drop. If each riser is 7 1/4 inches, how do we figure out how many risers that takes? Well, it's going to be 94 7/8. Add, subtract, multiply, divide, and what do we do? Say divide. Divide. There you go. We divide them. So 98 7/8 divided by 7 1/4. Again, here's one where your fraction calculator is going to be your best friend. But I'm going to go ahead and work this out the long way. 94 times 8 is 752. Plus 7 is 759. 7 1/4, how many fourths does that come out as an improper fraction? 29, good. So then, of course, we have to do what? Reciprocal, there we go. And we can cross cancel here. 8 and 4 both divide by 4 to give me 1 and 2. So then we do the 759 times 1 is 759. 2 times 29 is 58. Well, here's another one where we don't need the exact fraction. We just need a whole number, so we're going to divide. 759 divided by 58 gives us 13.08. Perfect. So if I round that down to 13 rises, will I have enough head clearance? No, I need at least 13.086. So I have to round up. So that'll be 14 rises. Now, the good news is that's really about all the work we have to do with fractions. We're going to look now at our back at our stairway. And I'm going to condense this. So if I'm going from here to here, and I need 14 rises, how many runs do I need? Well, just look at my little model here. I have 1, 2, 3, 4, 5 rises. I have 1, 2, 3, 4, 5 runs. So the number of rises is equal to the number of runs. So I need 14 runs or 14 treads. How big did we say our tread was going to be? 11 inches. So that's just going to be 14 times 11 inches, or 154 inches of stair opening. So what that means is, from the top of our stairs here to the front of our stair opening has to be 154 inches, or 12 foot 10 inches. Does that make sense? Now, what we learned with our fractions can actually help us to convert something like 54 inches into 12 foot 10. Because what we do is we just take our 154 inches and we put it over 12, and now it's feet. All we have to do is reduce that improper fraction. So it's 154 divided by 12. 12 does not go into 1. 12 goes into 15. How many times? Once. 1 times 12 is 12. We subtract to get 3, and we bring down the 4. 12 goes into 34. How many times? Twice, right? What's 2 times 12? 2 times 12 would be 24, and we have 10 left over. So just like when we did our improper fractions, where this number was the whole number and this was the number of whatever that fraction was left over. When we're doing measurement conversions, this is the feet, and the remainder is the inches. That's 12 feet, 10 inches. We'll look more at measurement conversions again later on in the course. I wanted to run this example past you because it really is kind of an intense example of using fractions in a construction application. Anybody have any questions? All right. Anybody have any questions off of the homework, those units? Would we have units 6 through 10? In the book? Perfect. So I gave you guys a quiz. We're going to hold off on doing that quiz until Friday. We'll work on that Friday when I'm over there. Just because I wanted to make sure I do this example, and I want to make sure you guys get a little bit of work time today, since I only gave you like 10 minutes at the end of the day Friday to do work time. But I do want to do, before we give you homework and work time here, I do want you guys to attempt one of these stair opening calculations. I will help you. You guys talk me through it. So what we're going to look at, we're going to do a floor. Let's say we're going to use floor trusses so they can be free spanned. So they're going to be thicker. We're going to have 22 3/4 of an inch thick. However, our lower level floor, which is often the case for a basement floor because the concrete gets poured above the base of the wall. Let's say that this is at 95 5/8 inches. We're going to end up with tread width of 10 3/4 inches. So first thing I want you guys to tell me how to do. How do I find my total floor-to-floor height? Okay, so the 3/4 becomes how many eighths? 6/8, right? So we add those together with the 95 5/8. 6/8 5/8 become 11/8, which is 1 3/8. Good. So we keep the 3/8, carry the 1. 1, 2, 5 makes 8. 2 and 9 make 11. Good. So that is my total floor-to-floor rise here, height. If I want my risers to be slightly more than 7 inches, how do I find how high each riser actually is? What do I need to find before I can find the actual height of the risers? Find number of risers. Good. How do I find the number of risers? Perfect. So 118 3/8. Now, I know that 3/8 as a decimal is 0.375, but if you didn't have a fraction calculator and you wanted to enter that, you just do 118 plus 3 divided by 8, and it'll turn it into 118.375. We divide by 7 to get 16.91. Now we still want to be a little bit more than 7 inches. So what are we going to use for a number of rises? 16 or 17? 16. Remember, rounding the number down gives us a larger unit rise. Perfect. So now we go back to the 118 and 3/8 and divide by what? 16 rises. We get 7.398. We need this to the nearest 16th. So we know that it's going to be 7 full inches. How do I take the 0.398 to get it to the nearest 16th?
Multiply it by 16.
There we go. Multiply by 16 to get 6.3, which is between 6 and 7, which will be closer to 6.375. Is it closer to 6 or is it closer to 7? 6. So that's 6/16, which of course reduces to 7 3/8 inches. So that's my unit rise or my riser height. Next, if I have 6'4" or 76-inch head clearance required, how do I find my total drop required from the top of the floor? Okay. So yes, the 76 plus 22 3/4. What's that add up to? Perfect. 98 3/4 inches. Perfect. So that's my total drop. So now I need to find the number of risers needed to achieve that total drop. How do I figure that out? You got it. 98 3/4 divided by 7 3/8. Since we're having so much fun, let's do this one out the long way. Let's make them in improper fractions. 98 3/4. Well, 98 times 4 is how much? 392. Good. Plus 3 is? Perfect. How about 7 3/8? How many eighths does that become? 59 eighths. Good. So now, what do we do next? There you go. Keep, change, flip. The reciprocal. You got it. Of course, we can cross cancel here. The 4 and the 8 is going to give us what? 1 and 2. Good. 395 times 2 is 790. 1 times 59, of course, is 59. And we have to divide that out. We'll go to the calculator for that. Giving us 13.389 or 390. And that is the number of risers required or rises needed. Do we round that up or down? up. So 14 rises. How many treads or runs do we need? 14, perfect. A lot of people make a mistake at this point because the number of rises equals the number of treads here. The reason they make a mistake is they a lot of times will subtract one, because in a total staircase, in an overall staircase, let's just look at a simple staircase like this. You have 1, 2, 3, 4, 5, 6, 7 risers, and 1, 2, 3, 4, 5, 6 treads. When you're looking at the full staircase, it takes one less tread than it does risers. So a lot of people subtract one from their risers to get the number of treads needed. But this isn't the full staircase. This is just to the stair opening. So we have to keep those numbers the same. So to find the size of the stair opening, what do we have to do? So we've got 14 and 10 3/4. What do we do with those? We are going to multiply them. So making improper fractions, 10 3/4 becomes how many fourths? 43, good. 14 is going to just become 14 over 1. Then what? Yep. We don't have to reciprocate because we're multiplying, but we can reduce. 4 and 14 were both divisible by 2. You don't have to do that. It just makes life a little easier. So it's 43 times 7. 301, good. 2 times 1 is 2. If we reduce that, that is 150 and 1/2. That is 12 foot 6 1/2. Or just we leave it as 150 and 1/2 inches. That is our stair opening. So that is how far we have to leave it open from the top of the stairs to where we begin our floor again, so that we make sure we have our minimum head clearance down here. Now, this assumes a couple of things. The first thing, the biggest thing it assumes, is that the floor thickness is going to stay full thickness and then just stop. Can anybody think of some things we could do to get some more floor space up here without losing head clearance? So this number, this floor opening, assumes that the floor stays full thickness and then it just stops right there at the edge of the opening. Can you think of anything we could do here to give us an extra floor space up top? What's that? We could taper the floor. So if you have your floor, let's say this is, well, in this case, it was what, 22 and a, that's a long ways up there. 22 3/4. That's a lot of floor. That's a lot of thickness. But what we can do is frame out a ways with decreasingly smaller pieces, structural pieces, and run that across. You have a joist on each side of the stair opening so you can run pieces across and run your floor out. Well, 22 3/4, we are looking here, we had 7 3/8 is the riser height, and 10 3/4 is our tread width. We could have that same ratio, this slope, we could have the same slope here and not compromise head clearance. So 7 3/8, that's basically 3 times that to get the 22. We could get almost 3 times the 10 inches. We could get close to 30 more inches up here by tapering the floor. Now, of course, there's a limiting factor. Can we actually go to a point here? Can we come to a perfect point up here? Not really. One, it's not a good idea to come to a perfect point because somebody's running and jumping on the stairways and hits their head on that. It's going to peel their scalp off. But the other limiting factor is structural. You have to have some sort of structural piece under there. In order to bring it to a perfect point, you'd have to have your sheetrock down below coming up past and your tongue and groove flooring up above coming past. If there's any sort of weight sitting right here, the flooring is going to flex, the sheetrock is going to flex, and the sheetrock's going to, at the very least, the sheetrock will break, but it's possible that the flooring will break as well. So at the very least, you have to stop where you're going to have a piece here, that this piece is large enough to be strong going across that width of the stairway. One exception to that I have seen done to get as much floor space up above as possible, and this was actually pretty ingenious, I thought. So there's your regular floor thickness down here. We have decreasingly small pieces going across. And they actually did bring it to a point here, but the reason we were able to do that is what we designed was there was actually a wall up above. And in that wall that was up above, so this wasn't really a sharp point, so if you're walking down and hit your head on it, it wasn't going to peel the top of your head off. But then in order to support the hat, I know that's a nice graphic for visual for the afternoon, isn't it? In the wall up above, we actually put a beam in the wall. So then we could screw up through the bottom of the flooring into that to hold the floor up. And so that there wasn't any flex up above and it didn't break. So it was still structural. It was bolted from the bottom up. That actually gave us several inches more floor space up above. The main reason we did it was so walls could line up. Okay, anyway, I am going to go ahead and shut up and give you guys some work time. So I cut you guys a little short on Friday working on units, was it 6, 7, 8, and 9, I believe. Actually, it was 7, 8, 9, and up through 10. So if you guys, we got about 8.5 minutes left. We'll go ahead and work on that. I have to cut off at 2:20 because that's when I have another class coming in at 2:30. Just so you guys are aware, I'm supposed to let you know that at the end of class, you guys are free to leave today, but you do have to make sure you go to the office and sign out. Okay. So I'm going to end the recording.